It's been pointed out that as amazing as these massive language models are at predicting just the next word, the way they learn feels a bit like trying to build a house brick by, well, painstaking brick.
Right.
There's this sense that it takes them far, far more data than a human needs to get to similar levels of language understanding. Okay, let's maybe unpack this a bit.
Yeah. And what's really fascinating here is the core objective.
Mm-hmm.
What these models are designed to do. Standard large language models, they're fundamentally trying to guess the immediate continuation of a sequence.
Mm-hmm.
Think about reading a book word by word, just constantly trying to anticipate what comes next right on the same line.
Exactly. And our focus today, really driven by some really interesting research, is on a different approach, multi-token prediction.
Okay.
So instead of just aiming for that single next word, the model tries to predict, say, n future words all at once.
Mm,
It's maybe more like trying to grasp the main idea of a sentence or even a short paragraph, not just the very next word in isolation.
right. Precisely.
Yeah.
And the central idea involves having a shared component within the model. You could think of it as a central processor, maybe that analyzes the input.
Okay.
And then you have multiple independent heads branching off from this central part. Each head works in parallel, trying to predict a different future word. The research paper we're looking at, it actually has a helpful diagram, figure 1, showing this setup pretty clearly.
Right. So the mission for this deep dive then is to get a solid understanding of how this multi-token prediction works under the hood.
Yeah.
And maybe more importantly, we want to explore why this could be a more effective route to building language models that are both, well, better at what they do and faster in how they do it.
Wow.
We're talking about a potential acceleration in AI capabilities here, and we really want to give you the essential breakdown.
And when we talk about better and faster, the research highlights several key advantages that are definitely worth a closer look. Like things like the potential for improved sample efficiency, which basically means the models could learn effectively from less data, enhance performance, particularly in demanding areas like coding,
Ah, coding.
and also the possibility of significantly quicker inference. That's the process of generating text after the model's been trained.
Okay, all right. So how does this predicting multiple words at once thing actually work then? Let's maybe start with what we already know. Standard next token prediction.
Hmm.
That involves minimizing a certain calculation of error, right? The paper called it L1.
Yes, exactly. The paper formally describes this in what they call equation 1. Essentially, the model is trying to maximize the likelihood of the single token that comes immediately next, given everything is processed so far.
Right.
It fine-tunes its internal settings, its parameters, to become increasingly accurate at this one-step-ahead prediction.
So when we talk about maximizing the probability, what does that practically mean for how the model learns? Like, what's it doing?
Well, it means the model adjusts its internal parameters to make the prediction of that one next word as certain as possible based on all the words that came before it.
Okay. Now, multi-token prediction changes this up. There's a new way of calculating error, LNN, which they detail in equation 2. What's the fundamental shift here?
Well, instead of just focusing on the probability of the immediately following word, the model now aims to maximize the combined probability of a whole sequence of future words.
Ah,
It's trying to predict not just word X, but word X and word Y and maybe word Z for a set number of future words, all based on the preceding text.
and to make this work, they use that shared central processor, the trunk we mentioned.
Exactly. It creates a single unified understanding, like a representation of the past context.
Uh,
And then those multiple independent heads each try to predict one of the upcoming words based on that shared understanding.
so maybe think of the shared trunk as like a team of detectives gathering all the clues from the past text.
Yeah, that's a good analogy.
And then the separate heads are like individual specialists, each focusing on predicting a specific aspect of what might come next based on that shared understanding of the clues.
Exactly right. And this allows for a breakdown, a factorization of the overall error or loss in multi-token prediction. It becomes the sum of the individual errors from each of those prediction heads. Equation 3 shows this.
Okay.
Each head is striving to get its particular future word correct, but they're all learning from the same foundational understanding of what came before.
Now, hang on. Trying to predict multiple words simultaneously. That sounds like it could really strain the memory capacity of our hardware, right?
Right.
Especially with the massive vocabularies these models use.
Oh, definitely.
How do they tackle those GPU memory demands?
Yeah, this is a really ingenious technical aspect of the paper. The most straightforward way, the naive way, to to calculate the probabilities for all those future words at once would indeed be very, very memory intensive.
Right.
The paper highlights their memory-efficient approach. I think it's in Figure 2.
Okay, so tell us how they managed to keep that memory usage in check. What's the trick?
Well, instead of doing all the calculations needed for prediction and learning the forward and backward passes for all the future word predictions at the exact same time,
Uh-huh.
they do it one after the other,
Mm.
sequentially. So after the central processor, the trunk, has done its initial work,
Okay.
they process each prediction head individually. They calculate the likelihood for that specific future word, figure out the adjustments needed for the model's settings,
Right.
and once that's complete, those temporary values, the activations, are cleared from memory before moving on to the next prediction head.
So it's like handling each prediction task sequentially, then cleaning up the workspace before tackling the next one. That sounds much more manageable.
It is.
And the paper mentions this significantly reduces the peak GPU memory needed.
Precisely. They were able to reduce the peak memory requirement quite substantially. The paper gives the specifics, going from something like ONV plus D down to OMV plus D, which is a big deal.
Right.
And crucially, they report that this didn't significantly increase the overall time it takes to train the model. This reduction is key because it lets researchers train much larger multi-token prediction models using the same hardware they already have.
Okay, so the how seems pretty clever. Smart engineering there.
Hey.
Now for the really interesting part, the why it matters. What concrete benefits did they actually observe when using this multi-token prediction method?
Yeah, the results. So the first major finding is that multi-token prediction appears to become increasingly advantageous as language models get bigger, as they scale up.
Okay.
They train models ranging from 300 million parameters all the way up to a pretty massive 13 billion parameters.
Wow.
And they train these on a huge data set of computer code, at least 91 billion individual code tokens.
91 billion tokens. Okay. And what did they see on those tough coding challenges? I think you mentioned Figure 3 in the paper shows some interesting results.
Yes. Figure 3 is quite compelling. For the smaller models they tested, the multi-token approach, well, it sometimes didn't perform quite as well as the standard next token prediction. A bit mixed.
Okay.
However, as they scaled up to those larger, more capable models, the trend reversed pretty dramatically. For instance, their 13 billion parameter model trained with multi-token prediction. I think it was predicting 4 tokens ahead solved, like 12% more problems on human evil and 17% more on MBPP, compared to a similarly sized model using only standard next token prediction.
12 and 17%. That's a really substantial improvement in performance. So bigger models seem to get a bigger benefit.
Exactly. It strongly suggests that for building truly powerful language models, especially for code, this technique could be a really significant step forward.
Okay, performance boost at scale. What about speed? You also mentioned it can lead to faster text generation, faster inference.
That's correct. Because the model has these additional prediction heads already built in from training, it can use a technique called self-speculative decoding during inference.
Self-speculative decoding. Okay, what's that?
So instead of generating just one word or token at a time, the model can use those extra heads to speculatively predict a few future tokens in parallel.
Oh, like having a few educated guesses ready before you're completely sure about the very first one?
Exactly. The main prediction, head number 1, generates its most likely next token.
Right.
And then the other heads offer potential continuations based on that same internal state. If these speculative tokens, these guesses, are deemed likely enough by the model itself, they can be accepted without needing a full, separate computation step for each one. This essentially reduces the total number of sequential steps needed to generate a passage of text.
And that speeds things up.
Considerably. They observe speed increases of up to 3 times faster with the model predicting 4 future tokens. Their 7B parameter model hit 3.0x speed up on code and 2.7x on text.
Wow, 3x faster. That's a huge gain in efficiency when you're actually using the model.
It really is.
And didn't they even explore an extreme version of this with byte-level tokenization? Tell us about that. That sounds interesting.
Yes, they did. To really push this idea that standard next token prediction might focus too much on very local patterns, they went to the extreme. They trained a 7 billion parameter model on individual bytes, the most fundamental units of digital information instead of whole words or subword pieces.
So much, much longer sequences then.
Exactly. Very long sequences, very fine-grained. And in this scenario, predicting 8 future bytes, so N8.
8 bytes. Okay.
It showed really remarkable improvements in solving coding problems compared to just predicting the very next byte, like 67% more problems passed on MBPP and 20% more on human evil.
Whoa, 67%.
Yeah. It really emphasizes how multi-token prediction can help models learn these broader patterns and these longer-range dependencies, even at a super fine-grained level.
And the speed up there.
Even more dramatic, they mentioned, I think, in the appendix table S2 and S3 reaching like a 6.4x speed up with that 8-byte prediction model.
That's quite a difference. So it really seems like looking a bit further ahead lets the model develop a better sense of the overall structure, doesn't it?
It certainly appears that way.
Now, the natural question then is, okay, how many future words or tokens should a model aim to predict? Is predicting, 10 or 20 always better? Where's the sweet spot?
Yeah, that's a crucial question. Is more always better? Not necessarily. They ran experiments specifically on this with 7 billion parameter models, trained on about 200 billion tokens of code. They tried predicting N01, the baseline, N2, N4, N6, and N8 future tokens.
Okay, and what did they find?
Their findings, shown in Table 1, indicate that predicting 4 future tokens, so N4, generally yielded the best results on those key coding benchmarks, human evil and MBPP.
So 4 was the winner for those tasks.
Generally, yes. However, they also found that for a different coding challenge, called APP and Intro, predicting 6 words, NA6, seemed to be optimal.
Huh.
It suggests that the ideal look-ahead window, the best N, might actually depend on the specific characteristics of the data the model is trained on, or maybe the downstream task itself.
Interesting that there seems to be an optimal range, not just more is better. What about training the models for longer, multiple epochs over the data? Do these benefits from multi-token prediction just disappear if you train for ages?
Good question. They did investigate this. And while the relative advantage gained from multi-token prediction might become somewhat less pronounced when the model is trained for many, many epochs,
Okay.
the multi-token approach still maintained an edge over traditional next-token prediction. So it seems to offer a lasting benefit, not just some kind of temporary boost early in training.
Got it. And this isn't just about training models from scratch, is it? What happens when you take an existing model and fine-tune it for a specific task, like those coding competitions you mentioned?
Right. This is another really important point. Does the pre-training method matter for fine-tuning?
Yeah.
The research demonstrates that initially, pre-training a model with multi-token prediction leads to better performance, even when you subsequently fine-tune that model on a specific task. In this case, they used a challenging coding competition dataset, code contests.
Okay.
And they observed, shown in Figure 4, that fine-tuning a model that was initially pre-trained to predict 4 future tokens, N4, clearly outperformed fine-tuning a model that was only ever pre-trained with standard next token prediction, N1.
So the multi-token pre-training gave it a better starting point for learning the specialized task.
Exactly. It indicates that multi-token pre-training helps the model learn more robust and, well, generally useful representations of information that transfer better to new related tasks.
Okay, so coding tasks seem to be a major beneficiary of this approach. We've seen strong evidence there. But what about natural language? The kind of text we humans use every day. How does multi-token prediction perform on more typical language tasks, like read and comprehension or question answering?
Yeah, that's the flip side. The results on standard natural language benchmarks were a bit more varied. They detail this in Figure 5 in Appendix G.
Varied how?
They found that predicting 2 future tokens, N2, performed pretty much comparably to the traditional next token prediction baseline on many standard NLP benchmarks, on par.
Okay, so N to 2 is fine.
But when they tried predicting 4 future tokens, N4, they actually saw a slight dip in performance on certain types of evaluations, like the MMLU benchmark.
Oh, really? A
Correct.
degradation. Why might that be?
Well, it seems like the longer range dependencies and the perhaps more structured nature of code benefit significantly from this multi-token look ahead. Natural language, though, with its, greater variability in phrasing, maybe more ambiguity, might require a more flexible approach. Predicting too far ahead could maybe introduce more uncertainty or lock the model into paths that aren't quite right for general language. Is that a fair assessment?
Yeah, that sounds plausible. The more open-ended nature of general language might mean that predicting too far ahead is harder or less useful. That's a bit surprising, though, given the really strong results in code.
It is, yeah. But the researchers do point out that these standard evaluations, these benchmarks, might not fully capture how well a language model can generate coherent and meaningful long-form text.
Okay, so maybe the benchmarks aren't telling the whole story for generation.
Potentially. When they looked specifically at tasks like summarizing documents, they found that both predicting N2, N4 future words actually led to improvements in RGL F1 scores, which is a key metric for summarization quality.
Okay, so better at generating summaries even if some of the standard test scores weren't always higher with M4. That's interesting.
Yeah, Figure 6 and Appendix 8 show those results. It suggests the benefit might be more apparent in generative capabilities.
What about the model's ability to reason in natural language, like solving math word problems?
They also explored this using a benchmark called GSM-8K, focused on natural language math problems. Appendix I, Figure S13 covers this. Interestingly, they found that with a smaller amount of training data, predicting two future words, N2, gave better results than next token prediction, NK.
And two better initially.
But this trend actually reversed when they used more training data. Then the N-1 baseline caught up and slightly surpassed N2.
Huh.
And the model predicting four future words, N4, generally didn't perform as well in this specific math reasoning area, regardless of data amount.
So it's really quite nuanced, isn't it? The optimal strategy seems to depend on the task, the data volume, the metric.
Absolutely.
Right.
It suggests that the best prediction strategy might not be one size fits all. It could depend heavily on the specific application and the training regime.
Okay, so we've seen the results, the performance, the speed-ups, the nuances. Now let's try and delve into the why. What's the underlying intuition? Why does predicting multiple tokens ahead seem to work so well, particularly for something like code?
Right, the mechanism. Their main idea, which they discuss quite a bit in Appendix L, is that multi-token prediction helps to bridge a gap.
A gap between what?
Between how these models are typically trained using a method called teacher forcing, where they're always shown the correct next word during the training process.
Like having the answers fed to them.
Exactly. And how they are used in practice, which is autoregressively. They generate text, one word at a time, and any errors they make can potentially compound and lead them down the wrong path.
Okay, I see the mismatch.
By forcing the model to predict further into the future during training, it's compelled to consider the longer-term implications of its predictions more directly. It has to anticipate not just the very next step, but the consequences a few steps down the line.
That makes intuitive sense. It's like learning to think a few moves ahead in chess, maybe, instead of just reacting to the opponent's last move.
Yeah, that's a decent analogy.
They also talk about choice points in the text, don't they? What's that about?
Yes, their argument, and they have a nice illustration in Figure 9, is that not all words or tokens are equally important or equally difficult to predict.
Right.
Some tokens represent crucial decision points, maybe the start of a new code block or a key variable name or a specific function call that significantly shape the subsequent text. While others are more predictable, maybe boilerplate code or common grammatical function words, more inconsequential, as they put it.
Okay.
They propose that multi-token prediction implicitly places more emphasis, more weight during the learning process on these critical choice points.
How does it do that?
Because if the model makes a wrong choice at one of these crucial points, the error becomes much more apparent, much larger when you're trying to predict several steps into the future based on that wrong choice. A small mistake early on can lead to big deviations later.
Ah, I see. So the penalty for getting a critical word wrong is effectively magnified because it messes up the predictions for several subsequent words.
Exactly. So by trying to predict further out, the model is implicitly encouraged to learn to focus more on getting those really important words right, the ones that truly matter for the overall coherence and correctness, especially in structured things like code.
That's a neat idea. Focus on what matters most.
Precisely. They also provide a more technical information theoretic argument in Appendix L2.
Okay, briefly, what's the gist of that?
Well, essentially, they show that predicting two future tokens, N2, mathematically increases the importance of the mutual information between consecutive tokens.
Mutual information, like how much knowing one token tells you about the next one.
Kinda, yeah. It makes the model better at predicting tokens that are actually relevant to the text that follows them, rather than just tokens that are likely given the past. It encourages learning forward-looking dependencies.
Interesting. So it helps the model anticipate better.
That's the idea, leading to more coherent and meaningful sequences overall.
And they didn't just rely on intuition, right? They ran some fascinating experiments on simplified sort of artificial data to try and isolate these effects.
Yes, the ablation studies on synthetic data. These were quite clever, designed to really probe specific reasoning abilities.
What did they find there? Tell us about the children's stories one first.
Okay, so in one set of experiments, they examined what they call induction capability. Basically, the ability to recognize and continue patterns based on recent examples. Like, if a character Alice is introduced, can the model then correctly predict Alice later in the story?
Right, basic pattern recognition and recall.
They trained small models on simple children's stories designed to test this. And they found that predicting two future words, and two, significantly improved the model's ability to learn and apply these induction patterns, especially for the smaller models they tested. Figure 7 shows this quite clearly.
So NT2 helps smaller models learn these basic patterns better.
Yes. But interestingly, they also noted in Appendix J, Figure S14, that this advantage seemed to lessen or even disappear when they used higher quality training data that perhaps already contained stronger signals for this kind of induction.
So maybe the multi-token prediction provides a greater advantage when the training data itself isn't perfectly suited, or maybe isn't extensive enough for learning certain patterns easily.
That's one interpretation, yeah. It might help the model extract those patterns more effectively, especially when the signal is weaker or the model opacity is limited.
Okay, interesting. What about more complex reasoning? Didn't they have a task involving math or algorithms?
Yes, for that, they use a task involving polynomial arithmetic, basically manipulating mathematical expressions according to set rules.
Right, a more procedural task.
Their results there, shown in Figure 8, indicated that multi-token prediction, again particularly N2 and NCL4, improved the model's accuracy across different levels of task difficulty.
Okay, better accuracy.
And importantly, it also enhanced its ability to generalize, to apply what it learned to slightly different out-of-domain situations.
Better generalization, too. That's key.
Yes. And notably, they found that this improvement from multi-token prediction was actually more significant than simply tripling the size of the model while sticking to next token prediction.
Wow. So changing the training objective had a bigger impact than a 3x size increase.
In that specific algorithmic task, yes. Figure S16 in Appendix K makes that comparison. They even experimented with adding special pause tokens to the input data in Appendix K, Figure S15, and found that multi-token prediction models still maintain their performance advantage.
That's really fascinating. It strongly suggests that predicting further ahead encourages the model to develop more robust and adaptable reasoning skills, not just memorize sequences.
It really does seem to suggest that. By looking beyond the immediate next step, the model appears to be learning something more fundamental about the underlying structure and the relationships within the data.
All right, this has been a great exploration. Let's try and synthesize all of this. If someone's listening, what are the key takeaways from our deep dive into multi-token prediction?
Okay, summary time. In essence, multi-token prediction looks like a very promising technique for training large language models. It seems to make them more efficient in their use of data, better sample efficiency.
Right.
It helps them achieve higher levels of performance, particularly in structured domains like generating computer code.
The coding results were strong.
And as a bonus, it opens up possibilities for significantly faster text generation, faster inference through this self-speculative decoding approach.
Yeah, the speed-ups were impressive.
And the underlying reason why seems to be linked to encouraging the model to prioritize those critical decision points in a sequence and enhancing its ability to anticipate relevant information that will appear later on. Better look ahead.
Nicely put. And the researchers themselves, they acknowledge this is still, an active area of research, right? What are some of the future avenues they mentioned exploring?
Yeah, they definitely see more work to be done. They're interested in exploring methods to maybe automatically determine the optimal number of future tokens to predict, perhaps using techniques that adapt during training based on how well the model is learning.
Dynamic alone. Okay.
They also suggest that the best vocabulary size for multi-token prediction might actually be different from what's optimal for standard next token prediction. Fine-tuning the vocabulary could lead to further gains.
Interesting point.
And finally, they're considering developing additional learning objectives, auxiliary losses that operate directly on the model's internal representations, the embeddings, maybe to further encourage learning these longer-range structures.
So lots more to explore there. It really feels like we're just scratching the surface of understanding the full potential here. This whole idea of looking ahead seems to offer some potentially fundamental advantages in how we train these incredibly powerful models.
It certainly does seem that way, which I think raises an important question, maybe a provocative thought for you listening. Given that predicting multiple steps ahead appears to be so beneficial, what are the ultimate limitations of this kind of look-ahead approach in language models?
Yeah.
Could this inspire even more radical departures from the traditional next word prediction paradigm in our ongoing quest for, truly intelligent AI? How far can we push this look-ahead idea?
That's a great question to ponder. How might this shift our understanding and even how we use these language models in the future? Definitely something worth considering.